All right, so let me go ahead and share the screen and we'll get started on activity 214. You guys see the power, or not, it's not technically a PowerPoint, but can you see the notes okay? All right, I'll give you just a couple minutes to get it put into your journals in the table of contents. It is again 214, and it's about Boolean algebra. All right, so Boolean algebra is used in digital electronics to simplify circuits. Sometimes if we do the process that we've been working on in 2.1.1 and 2.1.2 and 2.1.3, where we're building circuits based off of a design, it gives us a circuit that would work, but there can sometimes be a simplified version that we may or may not notice. Sometimes if you look at the min terms in your expression, you can see, oh, well, because of that and that, I could simplify. I don't actually have to have that. But usually it only helps you simplify the expression. It doesn't necessarily help you simplify the circuit directly. And so Boolean algebra is used, and again, like we said, for library terminology, for words, or for searching online, if you use in the search engine the terms and or not, things like that, you can focus in on your search. And that's exactly what we're doing in circuitry, is using and or and not or inverter gates. And so it makes sense that there should be some overlap. Now, the idea of Boolean algebra in this sense is to take a circuit that looks like this one here on the left. So we've got two inverters, three AND gates, and two OR gates that would give us the expression BC plus A naught B plus A naught C. But when we use Boolean algebra, we can simplify this expression down to A plus BC. And because we only need A plus BC, we can simplify the circuit down to what is shown here, which means instead of needing two inverters, three AND gates, and two OR gates, we only need a single AND and a single OR. All right, so that's the advantage. It's a cost-efficient way to build circuits, because we can start with, okay, well, what my output needs to be is BC plus A naught B plus A naught C. So we design it, figuring out what the output should be. Then we simplify it, and we realize, oh, I could design this bigger circuit that requires 3 different kinds of gates and 7 gates total. Or I could use this simplified version of it that only has 2 gates, and it'll accomplish the same thing. All right, so that's the goal. So as you can see here, it says Boolean algebra is a mathematical technique. And this is the part I would like you to have in your notes here. So I'll give you a few seconds to write it down after I read it through with you. Boolean algebra is a mathematical technique that provides the ability to algebraically simplify logic expressions. These simplified expressions will result in a logic circuit that is equivalent to the original circuit, yet requires fewer gates. So there's not really going to be a lot of writing down, but that couple of sentences I do want you to have in your notes. So I'll give you a couple seconds to write down those couple of sentences. While you're writing, I'm going to close the door. right, anybody need more time? Good? All right. So the name Boolean algebra comes from George Boole. So you don't actually have to know his name, but I thought you might be interested to know where this strange word comes from. So George Boole lived in England in the 19th century. He was a mathematician focusing on algebra and binary number systems. And since binary number systems ended up being used in computers well after his life, the name Boolean algebra was given to sort of honor him because he was one of the first mathematicians to really use a binary system even prior to the existence of true computers. So Boolean algebra is named after George Boole. That's why it has kind of a funny name. All right, now I'd like you to pause, and I'm going to actually switch my share here. I'm going to switch the share to Axis, and I want to show you something that I either want you to have open on a tab or I want you to print. Okay, so let me share Axis page with you. All right, can you see Axis now? Is it showing up all right? Okay. So I'm on the bulletin board page right now. You'll go to Topics, and then you'll see the 3 units that we have information on. Right now we're on Unit 2. Click on Unit 2, Combinational Logic. And then right now, if you want to look back at this PowerPoint, what I'm showing it to you in is Smart Notes. But most of you don't have the software to open a Smart Notebook file. So I do have the PowerPoint here, 214, Simplifying Circuits with Boolean Algebra. So if you need to go back and review, the PowerPoint is here on the left. But what I want you to download or open today is over here on the right. You can see a bunch of data sheets, which are going to be more helpful later. But right now, I want you to open this Circuit Simplification Equations. It has the Boolean algebra and something we're going to learn in the next unit called De Morgan's theorems. So if you'll open up this Circuit Simplification Equations, you will probably want to have a printed copy of it at some point just for ease of doing these problems. It's up to you, but if you were in class, I would give you a printed copy of it. So either open it in another tab and or print it, Circuit Simplification Equations. Once you open it, it should look like this. And so we're going to go today through these first 9 Boolean theorems. And then we're also going to talk about commutative, associative, distributive, and consensus theorems. So we're actually going to go through the first 19 of them. De Morgan's theorems is a completely another lesson. It's a completely different activity. So that one is 215 actually. So we won't be going over De Morgan's theorems today, but we will be going over 1 through 19. And just having this summary handy is extremely beneficial when you're doing this assignment. So whether you have it open on a tab or whether you have it printed, this is going to be kind of your best friend for completing this assignment. And you would never have to memorize any of this. If I give you a quiz over it, or if it's on part of a test, you'll always be given this document or be allowed to use it. You're not going to be asked to memorize it, but you do need to know how to use it. So that's the goal of 214, is to teach you what these are, show you how they work, and then give you practice using it. Because it's probably something that none of you have ever done before, or if any of you have, it's probably going to be very few of you. So, all right. So let me go back to the notes now. Hopefully all of you were able to find that document. Without the document, this assignment's going to be extremely difficult. So, all right. So if you can even follow along as we go through the notes, you'll be able to kind of follow along. We're going to go through them pretty much in order. In fact, I think they are exactly in order. And so if you want to kind of look at the paper and see the example on the screen. So the first 4 are single variable AND functions. So if you have an AND gate where one of them is a 0 and the other one could be whatever, could be on or off, it doesn't really matter. But if one of them is a 0 and it's an AND gate, the output has to be a 0. And if you understand how AND gates work, that makes sense, because if it's an AND gate, both the top and bottom inputs have to be on for the output to be on. right? So if even one of them is off, the other one will be off as well. So what this theorem tells us is if we are looking at an expression and there is a 0 in the expression, then we can simplify that to just 0. Okay, now when we go through some examples, it'll probably make a little more sense, but I want to help you kind of see how it fits with both the logic gate and then how it simplifies. So if you see an expression that has an x and a 0, an x times a 0, you can simplify that to a 0. And you may say, well, wait, Mr. Webb, we haven't seen any expressions with zeros in them yet. Well, you'll start to see them soon. So it'll make more sense, again, like I said, when we look at some examples. All right, theorem 2. If you have whatever this top input is and a 1 on the bottom, the output will be whatever that input on top is. If it's a 0, because it's an AND gate, then the output's 0 because they're both not on. If it's a 1, the output will be 1 because they both are on. So you could think through the logic of why these theorems work, but you don't want to take the time to think through the logic of why they work when you're trying to simplify a circuit. You want to just use them mathematically. So I'm trying to help you kind of understand why they work, but then we'll do the application of seeing how you apply it. Theorem 3 says if you have two inputs that are identical, the output will be whatever that is. So if you have x times x, you can simplify that to just a single x. Okay. And the fourth one, if one of them is on and one of them is off, like we see here, x and not x, then you can simplify that to off. Because if it doesn't really matter what x is, not is the opposite. So if x is on, the opposite is off. If x is off, the opposite is on, which means they're not the same, which means you're not going to get an on signal coming out. All right, so hopefully that logic, maybe you've worked enough with AND gates now that hopefully that logic makes sense as to why these can be simplified. But the application would be, if you see an expression that has x times x, simplify it to a single x. That's theorem 3. If you see an expression that has x times not x, theorem 4, you can simplify that to a 0. And then if that means you've got an x times a 0, you can go to theorem 1 and simplify that entirely to a 0. All right, so they're going to chain together. This is going to feel a little bit like geometry. I think probably many of you are either in geometry or you've had geometry. And if you've done proofs in geometry, that's what this is going to kind of feel like, is using these theorems to go step by step through a circuit expression and simplify. All right, let's look at the next set of theorems. These all involve OR gates. So they are single variable OR functions. And these are the next ones you see on your list here, 5 through 8 on your list. So if you have x or 0, then the output will be x. Because if x is a 0, they're both 0, so the output's 0. If x is a 1, the output's on because an OR gate is going to choose on if just one of them works. So if you have x plus 0 in your expression, you can simplify that to just x. If you have x plus 1, it doesn't really matter what x is. If the other one is 1, the output's going to be 1. If the other input is on, the output will be on because it's an OR gate. And remember, when we look at expressions, multiplication means it's an AND, addition means it's an OR. So if we have x plus a 1, we can simplify that to just a 1. If we have x plus an x, then it doesn't matter what they are, whether they're on or whether they're off, the output will be whatever x is. So you can simplify an x plus an x down to a single x. And then if you have an x plus a not x, since it's an OR gate, it doesn't matter what x is. If x is 0, not x is 1, so the output's 1. If x is 1, not x is 0, but the output's still 1. So if you ever have an x plus a not x, your output will be simplified to, or your output will be a 1, so you can simplify that expression to a 1. All right, so that is numbers 5 through 8 on your Boolean theorems. We're picking up speed a little bit here. Just one more to look at, and then we're going to start looking at some examples. Any questions so far? I don't want to go too fast that I'm confusing you, but I also don't want to bore you to death. So anybody have any questions? All right, so let's look at number 9 on your list. And this is something you haven't seen before. So this is like a double inverter, all right? So to have a double inverter, that's like saying you got a not, right? If you have a line over an X, that means not X. If you have a double line, that means it's not X. Okay, it's like two nots. It's a double negative. So circuit-wise, that would be you have X, you put an inverter, so now it's not X. You do another inverter, so now it's not X. All right, so if you ever have a not X, and this is really not going to be so important today, it's going to be more important with De Morgan's theorems next week, but I still want to introduce it today because it's number 9 on your list of Boolean theorems. It was one of those that came with Boolean algebra logic. So a double negative means it's going to be whatever X was originally. Okay, so if you have 2 lines over a letter, you can simplify that to just the letter, whatever it happens to be. All right, so those are your 9 theorems. 1 through 8 from this list will be the most important in today's lessons. And then number 9 will be more important next week when we look at De Morgan's theorems. All right, let's go ahead and walk through an example here. Hopefully you have your theorem list, okay, either digitally or in print, so that when we look at it step by step, you'll understand, oh, that's why this works. All right, so here's our first example. We've put together a circuit, and it's AAB. So we've got a triple AND gate with 2 A inputs and a B. And then we've got another triple AND gate with a C, a not C, and a D. And then those 2 triple AND gates are ORed together, right? If we were thinking about this as a circuit, it's a triple input AND with A, and B coming in, and another AND gate, triple input with C, not C, and D. And we use an OR gate to combine them together. That's what the circuit would be. But you can already see from this one, a double A doesn't really make sense. Why would we have 2 inputs of the same thing? Okay, so this one kind of is illogical, but it's hard to come up with examples when you can only use these first theorems. So some of them won't make a ton of sense when you look at the original, but it's to give you practice understanding how to simplify. So here is our solution. Here is the first step. Write down what you have. Write down your original expression. Now, looking at our theorems, if we look at theorem 3, theorem 3 says if you have x times x, just simplify it to x. So here we had a times a, so we simplify that to just a. So do we really need a triple AND gate? No, we only need a double input AND gate, right? So we're simplifying it down. All right, now if we look at theorem number 4, in the second part, we've got C times not C. Well, if we look at theorem number 4, when we have something times its inverse, we can simplify that to a 0. So that C not C becomes a 0. Any guesses to what theorem we're going to use next?
Theorem 1.
Why is that, Evan?
Because it's 0 times a variable.
Okay, so if we look at theorem 1 says 0 times a variable just simplifies to a 0. So here we've got 0 times d, that just simplifies to a 0. So anybody have any idea on what theorem we would use next?
Five.
Who was it that said that?
It was me, Harry.
Oh, hey, Harry. How did you pick 5, or why did you pick 5?
Because anything plus 0 is just that thing, and that's what 5 says.
Good. So theorem 5 says, hey, if you've got anything plus a 0, then it's just that thing. And so there we go. We've simplified it all the way down. So instead of an AAB plus C not CD, we can get that same result with just an AB. We would need a single double input AND gate. That's all we need instead of 2 triples and an OR. Questions about how these theorems help us simplify step to step? Are you following the process? Anybody have any questions about any of the steps? All right, let's try another one. Okay, here we've got four min-terms in our expression. We've got BB not C, B not C not C, not A B1, and A not B0. So again, we probably would never see an expression like this, but they're just trying to help you process the problem, process the theorems. Now, the order doesn't matter. So some of you might say, oh, I'm just going to start right away with BB not C, this first one, and use theorem 3, just like we did before. Some of you may say, you know what, I'm going to use a different one. I'm going to start with a different one. I'm going to use this AB1, and I'm just going to make that not AB. Some of you might say, well, I'm going to start with this A not B0, and I'm just going to make that 0, because anything multiplied by 0 is 0. So you could start with any of them. You don't have to do them in a certain order. So we'll walk through the solution to show you the order they chose, but just make sure you understand the order doesn't really matter as long as you eventually simplify all the steps down. So first step, obviously, write down the expression. And they chose first to use theorem 3 2 times. So you can see they took B and B are the same, so they simplified it to B. And then they took not C, those are the same, and they simplified it to not C. So they simplified both of these two expressions in one step because both of them use the same theorem. Double B becomes B. Double not C becomes not C. That's according to theorem 3. Questions on the first step? All right. Again, the order doesn't matter, but they've chosen next to go to theorem 7, which says if you have two things that are the same and you're adding them together, they just become the thing. So we've got B not C plus B not C. Those are identical and they're being added. So we can just write B not C. We don't have to have it on there twice. Because in a circuit, that would be B not C or B not C. Well, they're the same, so it doesn't matter. So they chose to simplify that one first. In their next step, they use theorem 2, which says anything times 1 is just that thing. So not AB times 1 is just not AB. So now we're running out of options. There aren't that many more things we can do. So the next step they chose was theorem 1. Anything times 0 is just 0. And then can anybody guess what theorem's left?
Theorem 5 again.
Theorem 5 again. Anything plus 0 is just the thing, right? That's theorem 5. So we got this plus 0 out here. We can just eliminate the plus 0. And so we've got B not C plus not AB. So we went from needing 1, 2, 3, 4 triple AND gates and 3 double OR gates. Now we only need 2 AND gates and 1 OR gate. So quite a bit simplified, a much simpler circuit, much more cost efficient as well. All right, any questions about these two examples or how to apply the first 8 theorems? All right, now we're going to go on to commutative, associative, and distributive laws and practice that. So these are just like what they mean in math class. So commutative laws, theorem 10, for AND gates, when you're multiplying two things, the order doesn't matter. So if switching the order helps, you can do that because multiplying 2 times 3 is the same as multiplying 3 times 2, right? Works the same in an AND gate. It also works the same in an OR gate. Adding 2 plus 3 is the same as adding 3 plus 2. It works just the same way in circuits. So the order doesn't matter when you're adding them together. So in other words, when you got a bunch of things multiplied together, rearranging the order to help you see patterns is fine. When you're adding a bunch of things together, rearranging the order to combine things is fine. All right, so that is theorem 10 and theorem 11, the commutative laws, just like in math. The associative laws are also just like in math. So if you're looking at an AND circuit and you've got x times y times z, you could group the y and the z, or you could group the x and the y. Now you don't have to group any of them, but the principle is if it helps to group them, go for it. And it doesn't matter which way you group them. Same thing for an OR function. If we're adding x plus y plus z, we could group the y and the z, or we could group the x and the y. It doesn't matter. They'll both work. And so these principles, they don't typically help quite as much. They're not quite as frequently used as some of the other ones, but every once in a while, just being able to group them can be helpful. And so just recognizing that just like in math, you can group them in any order is helpful. You have to follow the same principles as you would in math. Now the last set here, distributive property, is often very helpful. And it is also just like math class. So if you end up seeing an x times a quantity in parentheses, you can distribute the x, so x times y and x times z, just like you would distribute an algebra class. And if you have two binomials, if you're thinking about algebra terminology, if you got two binomials here, you probably have all learned the FOIL technique, right? So you can distribute x times w, x times z, y times w, y times z. First outside, inside, last, right? So you can just FOIL them out, and now you've got rid of all your parentheses and simplified down to just dual expressions. So the distributive laws are often used, and they work just like in math. So any questions on theorems 10 through 15? All right, let's put them to work. So here's our example. We've got not RT plus the quantity R plus not S times the quantity not R plus T. All right, so first step, obviously, write down your expression. And because we just talked about the distributive property, they are going to do that first. And they're going to use that theorem 15 using the FOIL technique. They're going to do R times not R times T, not S times not R, and not S times T. They're just FOILing it out first, outside, inside, last. All right, now we've got a set of 5 different expressions. Okay, so now we're going to use theorem 4. If we have an R not R, so in theorem 4, if we have something multiplied by its inverse, that's just a 0. So we can actually eliminate that one. Then we can use theorem 5. Whenever you're adding 0, you can just eliminate the 0 because it doesn't matter. So I'll pause there for a second. Any questions about the first 3 steps? And you can write these into your notes if you want, but you can also just open up the PowerPoint and look at it later if you want to go through these examples again. Or since I'm recording, you could go to the YouTube channel later once it's posted and watch the video if that's helpful. All right, in the next step, they've actually grouped and factored out a t. So this first term has a t in it, the second term has a t in it, and the third term has a t in it. So they've rearranged them according to the associative properties, and then they've factored out a t according to the 14th distributive theorem. So we factor out the t, and it leaves the not R from this one, the R from this one, and the not S from that one. Questions about that step? All right. Now, if we have an R and a not R added together, what theorem does that represent when we've got a variable with its inverse added together?
8.
8. So the not R and the R, according to theorem 8, can simplify to a 1. Now, when we have a 1 added to something, what theorem does that match up to?
2. Oh no. 6.
6, yeah. If we've got a 1 added to something, it just becomes a 1. So we can simplify that down. Now we can go to 2, right? Because a 1 times anything is just that thing. So we end up simplifying this one down to t plus not s not r. Questions on that example? All right. We've got one last group of theorems for today, the consensus theorems. And these are probably the least logical. I imagine the distributive property and associative and commutative properties, even though it feels weird maybe applying those here, it's just like what you've done 100 times in algebra class. Consensus theorems are not. So a lot of the theorems we've looked at so far seem pretty similar to what you would have learned in algebra, but these are not. So these you just basically have to start getting familiar with the patterns. So consensus theorem 16 says if we have an x plus a not xy, we can simplify that to just x plus y because it's an OR gate. This plus sign is an OR gate. So we've got x or not x. Well, the x is going to come through. So you can think it through logically, but most of the time you're just going to be looking for these patterns. In theorem 17, we've got x plus not y. Well, again, because it's an OR gate, the plus sign tells us an OR gate. If this x is here, that not x won't matter. So it's going to be x plus not y. So these two really got to go hand in hand. It's just basically saying it doesn't really matter what this y is. If there's an x plus a not x, you can eliminate that not x because it's an OR gate. So as long as one of them's on, you're going to get that on symbol coming through. In the 18th theorem, we've got a not plus an xy. It's not the x that goes through this time because it's an OR gate. It's the not x. Okay, it's the single one. So the not x plus the y is what would come through. And again, 19 is kind of the same pattern we saw a second ago. If it's not x plus x not y, it doesn't really matter what the y is. You can see in theorems 18 and 19, it doesn't matter what the y is. The combination you're looking for is that you've got a not x plus an x times something. So this x that's times the y, the not y, can cancel out. So we would get not x plus not y. So these you're looking more for patterns. You're trying to see, oh, I've got this plus the not version of it times something. Or here I've got a not something plus the something. So we're looking for that pattern to use the consensus theorems. And those are the last four for today. So we haven't really used theorem number 9, and we aren't going to learn 20 and 21 yet. Those are all going to be a big part of next week's lesson. Let's go to 14 and do an example. Now we've got everything you're going to have to be able to apply in today's lesson, and we'll see how we can simplify this one. So our example here, if we rewrite it, we've got P to PS plus P not Q not S plus PQS. So if we use theorem 14 first, we can factor out a P. Now they could have factored out a P from all three, right? But they factored out a P of the first two for a specific reason. Anybody recognize why they just chose the first two? Is there something in this set of parentheses that gets a pattern that's helpful?
Theorem 17.
Yeah, that theorem 17, we've got an S plus something times the not S. So when we see that plus with an S and a not S variable with its not added to it, multiplied by something else, we know we can eliminate that not. So it's theorem 17. All right, so by grouping them this way, they're setting up the ability to use theorem 17 and get rid of that not. All right. Now they can use theorem 14 and just distribute the P to the S and the P to the not Q and rewrite it. Now if they see, well, this first one has a PS, and this third one also has a P and an S, they factored out both the P and the S because it's in both of these. But when you factor PS out of itself, it just leaves 1. But when you factor PS out of PQS, it leaves the Q. So by grouping those two together and factoring out the P and the S, now what theorem can they use on this 1 plus Q?
Six.
Theorem 6. If we have theorem 6, 1 plus anything is just 1. And then now we've got 1 times this. What theorem tells us when we're multiplying 1 times anything?
2.
Theorem 2. And now we've got PS plus P not Q, and nothing can simplify. We could factor out a P, but it would leave S plus not Q. So there's no pattern there to simplify it any further. So instead of needing 5 gates as shown up here, now we just need 3. And before we needed 5 gates and 2 of them had to be triple inputs. Now we only need 3 gates and they're all dual. All right, so that is today's lesson. There's a couple more slides to wrap it up, but that's the content. The last bit here, it shows you, they want to emphasize to you that multiple methods can give you the same result. If I had said, hey, try this on your own, and then we compared yours to what they suggested, you may not have done the steps in the same order. So the point is, simplifying Boolean expressions can involve a lot of detailed steps or just a few combined steps. And so we're going to look back at example 4 and show just real quickly that you could actually do the steps differently and get the same result. So don't get hung up on, am I doing the steps in the right order? You didn't have to necessarily be in any order. So here you can see same 2 starting points, the example we just went through. In the example we just did, we used theorem 14 to group, and they started the same way. But then here, they went to theorem 17, like we did. That's the way we did it a minute ago. Here, they're saying, hey, you know what? We can actually use theorem 6, and they've grouped it differently here with theorem 14, same theorem, but they did a different grouping. They actually did this step down here first. So they're just doing them in a different order. The order doesn't matter. So we did 14 and 6 down here. They're starting with 14 and 6. We ended with theorem 2. They're actually using theorem 2 right here. And we started with 14 and 17. They ended almost with 14 and 17. And then they just distributed to simplify the final answer. So we used all the same theorems, but in a completely different order, and we get the exact same result. And so as you're doing these, don't worry about, well, I have to know which one comes next. No, you just have to figure out which one can come next. As long as it works, you can use it. You don't have to do it in a particular order. All right, any questions on the notes today? The last slide is just a summary. It's kind of organized funny. I like it better on the way that on the handout that I showed you before. It's the same thing though. I think this is just a little bit harder to see. All right. So you've got about 40 minutes left. So we're about halfway through the period. And your assignment, obviously 213 is what's due by midnight tonight, a little before midnight tonight. So if you haven't finished 213, make sure you're working on that today, getting that finished and submitted. And then as soon as you're done with that, begin working on 214. Now, you don't need to spend a ton of hours on 214 this weekend getting it done. I wanted to get the notes today because I know some of you are already done with 213. You've already submitted it and you're ready to go. So I wanted to get this lesson covered. Next, we don't have school Monday, so we meet next Wednesday. So next Wednesday when we're together again, you're going to have that whole period to do 214. So whatever you can get done in class today, great. And then you're going to have the whole period next Wednesday to continue working on 214. It's going to be probably kind of a time-consuming lesson for some of you. If you're super good at algebra, and especially if you're good at geometry and seeing patterns and proofs, probably won't have much trouble. But for some of you where that's not really your strong suit, it may take you some time. And for 214, if you look at the directions on OneNote, you'll see you do have to answer all the questions and the conclusions. So there's quite a few. So I'm giving you whatever time you have today to work on it, but also the entire period Wednesday. So Wednesday next week, we'll just meet together, take attendance. If you have questions, I'll take questions and you just have work time. So today, the rest of the time, you have work time, and I'll keep the Zoom running as always. We're more than halfway past the class time, so you don't necessarily have to check back in if you do log out, but you're welcome to if you want. If you want to stay logged in so that you can immediately ask questions and not have to go back and forth, that's fine. If you want to log out and just hope that you can get through it without needing any help from me, that's fine too. If you are logging out and I don't see you the rest of the period, hope you have a wonderful weekend, and I'll see you again next week.